Imagine a warship so advanced, so lethal, so packed with cutting-edge technology that naval engineers around the world stopped what they were doing and took notes. A destroyer that didn't just evolve naval warfare, it redefined it from the keel up. A steel giant born from the chaos of budget battles, political pressure, engineering nightmares, and sheer American determination. This is the story of the DDG Flight 3 destroyer, the most technologically ambitious surface combatant the United States Navy has ever attempted to build. And what happened between 2016 and 2025 is one of the most dramatic, most expensive, and most consequential chapters in modern military history. Stay with me, because what you're about to hear will completely change how you think about naval power in the 21st century. To understand why the DDG Flight 3 matters so much, you first have to understand the world it was born into. By the early 2010s, the United States Navy was staring down a growing nightmare. China was rapidly expanding its naval capabilities. Russia was modernizing its surface fleet with new anti-ship missiles. And the threats weren't just coming from state actors anymore. Rogue nations, terrorist organizations, and non-state actors were acquiring precision-guided weapons that could threaten even the most powerful ships afloat. The Navy's existing destroyers, as capable as they were beginning to show their age in one critical area: the ability to detect, track, and destroy incoming ballistic missiles and advanced cruise missiles simultaneously. The radars aboard earlier Flight I and Flight II destroyers, while impressive for their time, were reaching the limits of what they could physically do. The N/Spy, one radar system, a phased array marvel when it was introduced, was struggling to keep up with the volume and sophistication of modern threats. Something new was desperately needed, something revolutionary. And the answer, the Navy decided, would come in the form of a brand new radar, a brand new combat system, and a completely redesigned version of the most successful destroyer class in American history, the Arleigh Burke. The Arleigh Burke class had already proven itself as the backbone of American surface warfare. First commissioned in 1991, these ships had sailed through every major conflict and crisis of the post-Cold War era. They had launched Tomahawk cruise missiles into hostile territory. They had tracked and intercepted ballistic missiles in the Pacific. They had escorted carrier strike groups across every ocean on Earth. By the time planners began seriously sketching out what would become Flight 3, there were already dozens of Arleigh Burke destroyers in service, and the Navy wanted more. But not just more of the same. They wanted a quantum leap forward. They wanted a ship that could serve as the primary ballistic missile defense platform for the fleet, replacing older cruisers and allowing the Navy to retire aging Ticonderoga-class cruisers without losing critical air defense capability. This was not a small ask. This was an engineering challenge of enormous proportions. The centerpiece of the entire Flight 3 program, the technological heart around which everything else had to be redesigned, was the N/Spy 6 Air and Missile Defense Radar, commonly known as AMDR. And when you start digging into what this radar can actually do, the numbers become almost difficult to believe. The SPY-6 is not just an upgrade to the old SPY-1 radar. It is a generational leap. Engineers and program officials described it as being roughly 100 times more sensitive than the radar it was replacing. 100 times. Think about what that means in practical terms. Where the older radar might detect an incoming missile at a certain range under certain conditions, the SPY-6 could detect that same missile at a dramatically greater distance, giving the ship's crew and combat system precious additional seconds, sometimes minutes, to respond. In modern naval combat, those extra seconds are not a luxury. They are the difference between a successful intercept and a catastrophic hit. The SPY-6 uses gallium nitride semiconductor technology in its transmit and receive modules, a material that allows for far greater power output and far greater sensitivity than the older gallium arsenide technology used in the SPY-1. Raytheon Technologies, the primary contractor for the radar, spent years developing and refining this technology, and the results were staggering. But here is where the story starts to get complicated. and where the drama of the Flight 3 program truly begins to unfold. The SBY-6 radar is massive. It is physically large and extremely power-hungry, and this created a cascading series of engineering problems that threatened to derail the entire program before a single ship was ever laid down. The Arleigh Burke hull, as brilliant a design as it is, was never intended to carry a radar of this size and power consumption. The ship's electrical generation capacity, its structural layout, its topside weight distribution, all of it had to be fundamentally reconsidered. The Navy and its contractors at Huntington Ingalls Industries and Bath Iron Works faced a choice. Either redesign the ship so extensively that it effectively became a new class entirely, which would cost enormous sums of money and add years to the program, or find ways to squeeze, adapt, and engineer around the constraints of the existing hull. They chose the latter path, and executing that choice became one of the most technically demanding shipbuilding challenges of the modern era. The topside weight problem alone consumed years of engineering effort. The SBY-6 radar arrays are heavy. Adding that weight high up on the superstructure of a ship affects its stability, its roll characteristics, its seakeeping ability in rough weather. Naval architects had to conduct exhaustive stability analyses and then implement compensating measures throughout the ship's design. Weight was removed from other areas wherever possible. The superstructure was redesigned. The mast configuration was altered. Every pound that could be saved elsewhere was saved, because every pound saved meant more margin for the radar and its associated systems. This kind of engineering work is painstaking, unglamorous, and absolutely critical. It happens in offices and computer simulation labs long before any steel is cut, and it determines whether a ship will perform as advertised or whether it will roll uncomfortably in heavy seas and underperform on every mission. The electrical power demands of the SBY-6 system also forced a major redesign of the ship's power generation infrastructure. The older destroyers simply could not generate enough electricity to run the new radar at its full potential while simultaneously powering all the other systems a modern warship requires: propulsion, weapons systems, communications, crew life support, damage control systems, and everything else. The solution was a new integrated power system featuring upgraded gas turbine generators capable of producing significantly more electrical power than those on earlier flight variants. This wasn't just a matter of swapping in bigger generators, either. The entire electrical distribution system aboard the ship had to be redesigned to handle the increased power loads, and to ensure that power could be reliably delivered to the radar and weapons systems even in the chaos of combat. Even with multiple systems running at full capacity simultaneously, and even if some components were damaged in action. Now, while all of this engineering work was proceeding, the program was simultaneously navigating a treacherous political and budgetary landscape in Washington. The years between 2016 and 2025 were not politically calm years for American defense procurement. Budget pressures, continuing resolutions, debates over defense priorities, and the ever-present tension between what the Navy wanted and what Congress was willing to fund created a constantly shifting set of constraints that program managers had to work around. There were moments when the future of the Flight 3 program looked genuinely uncertain. Critics questioned whether the investment was justified. Some analysts suggested that the Navy should pursue alternative platforms or different technological approaches. Others worried that concentrating so much capability in a single ship type created dangerous vulnerabilities. These debates were not idle academic exercises. They had real consequences for funding, for schedules, for the number of ships ultimately authorized and built. The relationship between the Navy and its two primary shipbuilders, Huntington Ingalls Industries, which builds destroyers at its Ingalls shipbuilding facility in Pascagoula, Mississippi, and Bath Iron Works in Bath, Maine, a subsidiary of General Dynamics, was also a source of significant tension and challenge throughout this period. Shipbuilding is extraordinarily complex, and the introduction of the Flight 3 modifications added layers of complexity to an already demanding manufacturing process. Workers had to be trained on new systems and new construction techniques. Supply chains had to be established for components that had never before been integrated into a destroyer. Quality control systems had to be adapted and expanded. And all of this had to happen while both shipyards were also building earlier flight variants and dealing with their own internal challenges, including labor shortages, workforce training issues, and the constant pressure to deliver ships on time and within budget. Bath Iron Works, in particular, faced significant challenges during this period that became a major story in themselves. The shipyard, which has been building Navy vessels since the 19th century, struggled with productivity issues and schedule delays on destroyer construction that attracted considerable attention from Congress and from Navy leadership. Investigations and reviews were conducted. New management approaches were implemented. Labor management tensions surfaced publicly in ways that were uncomfortable for all involved. The COVID-19 pandemic, which hit hard in 2020, added yet another layer of disruption to an already stressed shipbuilding enterprise. Supply chain disruptions, workforce absences, and the practical difficulties of maintaining complex manufacturing operations during a public health emergency all took their toll on schedules and costs. Understanding these industrial realities is essential to understanding why the Flight 3 program evolved the way it did, because the best radar technology in the world means nothing if the ships carrying it cannot be built efficiently and reliably. The first Flight 3 destroyer, USS Jack H. Lucas, designated DDG 125, was laid down at Huntington Ingalls Industries Ingalls Shipbuilding Division in Pascagoula, Mississippi in June 2019. The laying of the keel is a ceremonial and practical milestone in shipbuilding. It marks the moment when the ship's construction formally begins and the first sections of the hull are assembled in the dry dock. For the Flight 3 program, this was a moment of genuine significance, the culmination of years of design work, engineering analysis, budgetary battles, and industrial preparation. The ship was named in honor of Jack H. Lucas, one of the most remarkable heroes in American military history. A Marine who survived throwing himself on 2 grenades during the Battle of Iwo Jima in World War II, and who received the Medal of Honor at the age of 17, the youngest Marine to receive that honor in the 20th century. It was a powerful name for a powerful ship. The construction of DDG 125 proceeded through a series of phases that reflected the enormous complexity of modern naval shipbuilding. The hull was assembled from large prefabricated sections called modules, each of which was constructed separately before being joined together in the dry dock. This modular construction approach allows shipyards to work on multiple sections of a ship simultaneously, improving efficiency and reducing overall construction time compared to sequential construction methods. But for Flight 3, many of these modules contain new systems and new arrangements that workers and supervisors were encountering for the first time. The learning curve was real, and it had real costs. The integration of the SPY-6 radar into the ship's superstructure was one of the most challenging aspects of the construction process. The radar consists of multiple large array faces that must be precisely positioned and aligned, then connected to an enormously complex network of cables, cooling systems, power distribution equipment, and signal processing hardware. The physical installation of these components required new tooling, new procedures, and new quality verification processes. Getting everything right the first time was not always possible, and rework, the expensive and time-consuming process of correcting construction errors, was a persistent challenge. This is not unusual in the construction of genuinely novel complex systems, but it added to costs and contributed to schedule pressure. The Combat System Integration Challenge deserves particular attention because it gets to the heart of what makes the Flight 3 destroyer different from everything that came before it. The Aegis Combat System, which is the integrated command and control and weapons system at the center of Arleigh Burke destroyers, had to be substantially upgraded to take full advantage of the SPY-6 radar's capabilities. The new Aegis Baseline 10 system, developed specifically for Flight 3, represents a fundamental redesign of the combat system software and hardware architecture. It is not simply a software update to the older Aegis baselines. It is a new system that was designed from the ground up to process the dramatically increased data flow coming from the more sensitive radar and to make faster, more accurate engagement decisions in a more complex threat environment. Software development for naval combat systems is one of the most demanding areas of software engineering in existence. The code must be extraordinarily reliable. System failures in combat can be lethal. It must be fast enough to process radar data and make engagement decisions in fractions of a second. It must be secure against cyber intrusion. And it must be testable in ways that allow the Navy to have genuine confidence in its performance before the ship goes anywhere near a real threat. The development and testing of Aegis Baseline 10 consumed enormous resources and generated its own set of challenges and delays. Testing facilities had to be set up and certified. Scenarios had to be developed that would stress test every aspect of the system's performance. And when problems were discovered, as they inevitably were, they had to be diagnosed, corrected, and retested in a process that could take months. One of the most important testing milestones for the Flight 3 program came in a series of live-fire exercises conducted at the Pacific Missile Range facility in Hawaii. These tests, which involved launching actual target missiles and attempting to intercept them with the DDG Flight 3's combat system and weapons, provided the most realistic assessment available of how the new ship would actually perform in combat. The results of these tests were closely watched by Navy leadership, by Congress, by allied nations, and by potential adversaries. Every intercept success strengthened the case for the program. Every failure, and there were some, as there always are in honest, rigorous testing, generated scrutiny, analysis, and pressure to improve. The weapons systems carried by the Flight 3 destroyers also deserve careful examination, because the ship's offensive and defensive capabilities extend well beyond the radar. The vertical launch system, which consists of large cells embedded in the ship's deck that can hold a variety of different missiles depending on the mission, remains the primary weapons delivery mechanism. Flight 3 destroyers carry 96 VLS cells in two groups, a forward group of 32 cells and an aft group of 64 cells. These cells can be loaded with a combination of standard missiles for air defense and ballistic missile defense, Tomahawk cruise missiles for long-range strike, ASROC anti-submarine rockets, and potentially other weapons as they become available. The flexibility of the VLS system is one of its great strengths. The same physical launcher can accommodate many different weapons, allowing the ship to be reconfigured for different missions. The Standard Missile program was itself undergoing significant evolution during the Flight 3 development and production period. The SM-6, which provides extended-range anti-air warfare capability and limited anti-ship capability, was becoming a critical component of the Flight 3's expected mission set. The SM-3, particularly in its Block IIA variant developed jointly with Japan, was the primary ballistic missile defense interceptor, and newer developments in the Standard Missile family promised even greater capabilities in the years ahead. The ability of Flight 3 destroyers to employ these weapons to their full potential, enabled by the superior tracking and discrimination capability of the SPY-6 radar, was the core promise of the entire program. The international dimension of the Flight 3 story adds another layer of richness and complexity. The United States was not building these ships in isolation. Allied nations were watching closely, and many were considering their own upgrades to their surface fleets. Japan, South Korea, Australia, Spain, and Norway, all operators of Aegis-equipped destroyers or frigates, had a keen interest in the SPY-6 radar and in the lessons being learned from the American Flight 3 program. Japan, in particular, was a deeply invested partner, having jointly developed the SM-3 Block IIA interceptor with the United States and having built its own fleet of Aegis destroyers that could potentially benefit from SPY-6 integration. The technology transfer and industrial cooperation dimensions of these relationships were sensitive and complex, involving both the sharing of genuine capability with trusted allies and the protection of the most sensitive technologies from potential adversaries. China's reaction to the Flight 3 program, while never publicly stated in complete detail, could be inferred from the trajectory of Chinese naval investments during this same period. China accelerated the development and deployment of its own advanced anti-ship missiles, hypersonic weapons, and electronic warfare systems throughout the years when Flight 3 was being developed and built. Chinese naval planners clearly recognized that a more capable American destroyer force would require more sophisticated countermeasures. The result was a technological competition played out over years and across multiple domains. A naval arms race conducted in shipyards and laboratories rather than on the high seas, but no less consequential for that. The hypersonic threat, in particular, became an increasingly prominent concern for Flight 3 planners as the program matured. Both China and Russia demonstrated hypersonic glide vehicles and hypersonic cruise missiles during this period that represented a genuinely new category of challenge for naval air defense systems. These weapons fly at speeds of Mach 5 or above, following unpredictable flight paths that make them difficult to track and intercept. The question of whether the Flight 3 destroyer, with its powerful spy, 6 radar, and Aegis baseline 10 combat system, could effectively engage hypersonic threats became one of the central questions of naval warfare planning. The answer, as of the mid-2020s, was nuanced. The radar provided unprecedented tracking capability, but the interceptors available to the ship had limitations against the fastest and most maneuverable hypersonic threats. This drove investment in new interceptor development, including directed energy weapons research, though none of these were mature enough to be integrated into the initial Flight 3 production ships. Directed energy weapons, high-powered lasers, and high-powered microwave systems were another technology area that was being actively explored for future incorporation into destroyers during this period. The Navy's interest in laser weapons was driven by their potential to provide essentially unlimited magazine depth compared to the finite number of missiles a ship can carry, and by their ability to engage threats at the speed of light, eliminating the intercept timing challenges associated with kinetic weapons. Demonstrator systems were tested on surface ships during this period, and the results were encouraging enough to fuel continued investment. But the power demands of militarily useful laser weapons remained a significant challenge for integration into existing hull forms, making them a technology for future ship variants rather than for the initial Flight 3 production run. As construction of the first Flight 3 ships progressed, the program's status became a barometer of the broader health of American naval shipbuilding. Delivery schedules, cost performance, and sea trial results were scrutinized by Congress, by the Navy, by defense analysts, and by journalists with unusual intensity. Every milestone, every successful systems test, every hull launch, every commissioning ceremony was a data point in the ongoing assessment of whether the program was delivering on its promises. And to be honest, the record was mixed. There were genuine achievements and genuine shortfalls. Systems that performed better than expected and systems that required more refinement. Ships that were delivered on schedule and ships that were delayed. The overall trajectory was one of gradual progress toward the program's goals, but that progress was rarely smooth or linear. The commissioning of USS Jack H. Lucas in 2023 was a milestone moment for the program. After years of design, construction, testing, and refinement, the first Flight 3 destroyer officially entered the United States Navy's fleet. The commissioning ceremony was held with appropriate ceremony and recognition of the significance of the moment. Navy leadership spoke about the ship's capabilities and what they meant for American naval power. The crew, who had spent months training on the new systems and preparing for their first deployment, was a visible symbol of the human element in a program that could easily become reduced in public discussion to specifications, cost figures, and technology acronyms. These were real sailors, trained professionals who would take this remarkable ship to sea and operate it in the real world, far from the comfortable certainties of test ranges and simulation labs. The operational testing and evaluation phase that followed commissioning was in many ways the most important test of all. Operational testing is different from developmental testing. It is conducted under conditions that simulate real-world operations as closely as possible, using actual Navy operators rather than contractor or government testing personnel, and it is designed to reveal any issues that might not have been caught in earlier, more controlled testing environments. The results of operational testing would determine whether the ship was truly ready for combat deployment, and they would also generate lessons that would inform the construction and fitting out of the subsequent Flight 3 ships in the production pipeline. The production pipeline itself was a story of its own. Multiple Flight 3 destroyers were in various stages of construction simultaneously at Huntington Ingalls Industries and Bath Iron Works during the heart of the program. Managing the flow of materials, components, and skilled labor across two geographically separated shipyards, both building the same new type of ship for the first time, required coordination and industrial management capabilities that were tested to their limits. The Navy's Program Executive Office for Ships, which has oversight responsibility for destroyer acquisition, worked continuously to identify and resolve bottlenecks, to share lessons learned between the two yards, and to manage the inevitable tensions between schedule pressure, cost control, and quality requirements. Workforce issues were a persistent challenge throughout the production period. Naval shipbuilding requires an extraordinarily skilled workforce: welders, pipe fitters, electricians, structural mechanics, combat systems technicians, and dozens of other specialties, all of whom must meet rigorous quality standards and security requirements. Building and maintaining this workforce is not something that can be done quickly. It takes years to develop the skills and experience needed to work on complex naval vessels, and the workforce that builds today's ships is the product of investments in training and apprenticeship programs that were made years or even decades earlier. Both shipyards invested heavily in workforce development during this period, recognizing that their ability to execute the Flight 3 program and future programs depended fundamentally on having enough skilled people to do the work. Supply chain management was another area of intense focus and ongoing challenge. A modern destroyer contains hundreds of thousands of individual components sourced from suppliers across the United States and, in some cases, internationally. Managing this supply chain, ensuring that the right components are available at the right time, that quality standards are met at every step, and that single-source suppliers who could hold up production are identified and managed, requires industrial capabilities that rival those of the most complex commercial manufacturing enterprises. The disruptions of the early 2020s, including semiconductor shortages that affected industries from consumer electronics to automobiles to military electronics, highlighted the vulnerabilities in defense supply chains and drove significant effort to identify alternatives and build greater resilience into the supply network. The electronic warfare capabilities being integrated into the Flight 3 destroyers also deserve attention, because in modern naval combat, the ability to detect, characterize, and disrupt enemy electronic emissions is at least as important as the ability to shoot missiles. The N/SLQ-32 electronic warfare system, in its most updated versions, provided the ship with the ability to detect radar and communications signals from potential threats, to characterize those signals and identify the platforms emitting them, and to jam or disrupt those signals in ways that could degrade the enemy's ability to target the ship. The integration of this system with the combat system meant that electronic warfare information could be fused with radar and other sensor data to provide a more complete picture of the threat environment. As adversary electronic systems became more sophisticated, so too did the countermeasures being developed and integrated into the Flight 3 ships. Cybersecurity was a topic that received growing attention throughout the development and production period, as the vulnerability of networked military systems to cyber attack became increasingly well understood. The Aegis Baseline 10 combat system, like all modern military systems, was designed with cybersecurity in mind from the earliest stages of development. But the cyber threat environment evolves rapidly, and ensuring that systems remain secure against the most current threats requires continuous effort. The Navy established rigorous cyber testing and assessment processes for the Flight 3 program, subjecting the combat system to simulated attacks by red teams that attempted to find and exploit vulnerabilities. This was uncomfortable work that sometimes revealed concerning vulnerabilities, but it was essential to ensuring that the ships would be able to operate effectively in a contested cyber environment. The relationship between the Flight 3 program and the broader questions of American naval strategy during this period was profound and sometimes contentious. The Navy's 2016 Force Structure Assessment, which called for a fleet of 355 ships, set an ambitious goal that the service struggled to fund and execute throughout the following decade. Destroyers were a central part of this plan, and the Flight 3 variant was intended to be the primary production type for new destroyers well into the future. But the cost and complexity of each Flight 3 ship, combined with the challenges at the shipyards, meant that the Navy was never adding destroyers to its fleet as rapidly as the strategic plans called for. Ships were being retired at rates that sometimes exceeded the rate of new construction, and the overall size of the surface combatant fleet remained a subject of intense congressional and public scrutiny. Some voices in the defense analysis community argued during this period that the Navy was making a mistake by concentrating so much investment in large, expensive, exquisite surface combatants like the Flight 3 destroyer. They pointed to the rapid proliferation of anti-ship missiles in the hands of potential adversaries and argued that large surface ships would be increasingly vulnerable in a high-end conflict environment, particularly in confined waters like the South China Sea or the Taiwan Strait. They proposed alternatives, smaller, cheaper, more numerous vessels that could saturate enemy defenses through numbers rather than trying to survive through the sophistication of their own defensive systems. These arguments were taken seriously by some naval planners and less seriously by others, and the debate they generated about the future of surface warfare was one of the most important intellectual conversations in American defense policy during this decade. The Navy's response to these arguments was essentially to pursue a both-and strategy rather than an either-or choice. The Flight 3 destroyer program continued as planned, as the high-end backbone of the surface fleet's air defense and ballistic missile defense capability. But the Navy also invested in the development of smaller surface combatants, including the Constellation-class frigate, which offered a lower-cost option for less demanding missions and could be built in larger numbers to increase the overall size of the fleet. The frigate program itself was not without controversy and challenge, but its existence reflected a recognition that the destroyer force alone could not be large enough to meet all of the Navy's global commitments. As we move toward the conclusion of our examination of this program, it is worth stepping back and considering what the DDG Flight 3 destroyer program tells us about the state of American military technology, American industrial capability, and American strategic thinking in the early 21st century. The program is in many ways a microcosm of the broader challenges facing American defense. The tension between technological aspiration and fiscal reality, between the desire for exquisite capability and the need for affordable quantity, between the pace of technology development and the slower rhythms of shipbuilding and weapons development. These tensions are not unique to the United States. Every major naval power faces versions of the same dilemmas. But the scale and ambition of the American response, embodied in the Flight 3 program, is unique. The SBY-6 radar that sits at the heart of the Flight 3 destroyer is, by any reasonable assessment, the most capable air and missile defense radar ever installed on a surface combatant. Its ability to track multiple threats simultaneously, to discriminate between genuine threats and decoys, to operate effectively against both aerodynamic and ballistic targets, And to do all of this in a heavily contested electronic warfare environment represents a genuine and significant advance in naval capability. The adversaries who must plan against it know this. The allies who want access to it know this. And the American taxpayers who funded its development deserve to know it too. The ships themselves, USS Jack H. Lucas, and the growing number of Flight 3 destroyers that have followed her, are extraordinary vessels. They are the product of the work of tens of thousands of Americans. Engineers, scientists, shipyard workers, sailors, program managers, and the countless others who contributed their skills and dedication to bringing these ships into existence. They represent a bet that American technological superiority can be maintained through investment and ingenuity, and that surface naval power remains relevant and potent even in an era of proliferating anti-ship missiles and growing cyber and space-based threats. Whether that bet pays off will ultimately be decided not in shipyards or test ranges, but in the actual operational environment. In the waters of the Western Pacific, the Persian Gulf, the Mediterranean, and wherever else American destroyers are called to operate. The crew of a Flight 3 destroyer standing watch in a contested environment, tracking ballistic missiles with the SPY-6 radar, and preparing to engage them with standard missiles, will be the ultimate test of everything this program has attempted to achieve. And the verdict of that test, should it ever come in a real conflict, which we must sincerely hope it never does, will be delivered not in budget documents or program reports, but in the language of survival and performance under fire. The story of DDG Flight 3 is ultimately a human story, a story about the people who conceived this program, fought for it, built it, and sailed it. It is about the engineers who spent years solving problems that had never been solved before. It is about the shipyard workers who learned new skills and new processes to build something genuinely new. It is about the program managers who navigated years of budget battles and schedule pressures without losing sight of the goal. And it is about the sailors who will take these ships to sea and trust their lives to the technology and craftsmanship of those who came before them. That is the real measure of any weapons program, not the specifications or the cost figures, but whether the people who depend on it can trust it when it matters most. The decade from 2016 to 2025 was a defining period for American surface naval power. The decisions made, the technologies developed, the ships built during those years will shape the United States Navy's capabilities for decades to come. The Flight 3 destroyer is not the final word in surface naval warfare. No single platform ever is. But it is a remarkable achievement in a field where remarkable achievements are genuinely difficult, genuinely expensive, and genuinely consequential. The next chapter of this story is still being written, in the waters of the world's oceans, by the crews of ships that represent the best that American naval engineering has ever produced. Now, here is the question I want you to think about and share in the comments below. Given the extraordinary cost of each Flight 3 destroyer, approximately $2 billion per ship, do you believe the United States Navy should continue building these advanced but expensive destroyers, or should it shift investment toward larger numbers of smaller, less expensive vessels to counter the growing missile threats from China and Russia? What strategy do you think gives America the strongest naval future? Drop your answer below, because this debate is shaping the future of American sea power right now, and your perspective matters. And if this deep dive into one of the most ambitious naval programs of our time gave you new insight into how modern warships are built and why they matter, please hit that like button and subscribe so you never miss another exploration of the technologies and decisions that shape our world.